Steven Stevens and Fades, Troops, Lottos, and BKs, those was the days. High-tech boots, spray painted with your names. T-shirts, airbrush, they read the same. Thick herringbone chain.
In this video, I will talk you about energy approach for a simple harmonic oscillator. To solve certain problems, it is not always necessary to use the sinusoidal forms that we learned earlier. So there are two types of energy included in our spring mass system. First is the energy stored in the spring as it's being stretched or compressed. And that is called the potential energy of the spring, denoted by U. And that is half times spring constant K times the amount of compression or stretch of the spring to the second power. And there's also kinetic energy in the mass as it's moving, and that is denoted by K. And you are probably familiar with this formula already. Half m mass of the object times its velocity. So the total energy of the spring mass system is always E equals U plus K, which is half kx squared plus half mv squared. Let's have a look at these figures shown here. So in the first one, the mass has been pushed to a position where x equals minus a. So let's compute or calculate the energy in that position. So E equals half k times the displacement x, which in this case is minus a. Oops. Squared plus the kinetic energy half m times v. But because the mass is not moving, the v is 0, so we have nothing for that. So there we get the energy to be 2 times k times amplitude squared, which is also shown here. Now the situation changes when the mass starts moving and it picks up velocity. Next, let's have a look at the situation where the mass is at the equilibrium position. What is the energy then? Again, E is half times k times the displacement, but at this point the displacement is 0, so we have 0 squared plus its velocity, whatever it is, squared. So the potential energy term goes to 0, so we have 2 times mv squared. And this is in fact the maximum velocity the mass will ever have, as we know from previous chapter already. So it can be denoted as v max, also shown here. Energy-wise, the third case is same as the first case, where all of the energy is in the spring's potential energy. And in the fourth case, we have the most common one, where the energy has been divided in some way between the kinetic energy, K, and the potential energy of the spring, U. The key thing to understand from these figures is that the energy E is always constant. Its amount doesn't change. Only how that energy has been divided by the spring and the mass changes. For example, in this first case, all of the energy E has been stored in the compression of the spring, so we only have potential energy U here. The K, kinetic energy of the mass, is 0. On the other hand, in the second case, when the spring is at its rest position, so it's not either compressed or stretched, there's no energy stored in the spring whatsoever. All the energy of the system is in the velocity of the mass, and hence we have only kinetic energy K. The most common case is, of course, when the mass is somewhere in between the amplitude position x equals a or the equilibrium position x equals 0. So in that case, part of the energy is stored in the spring and part of it is stored in the kinetic energy of the mass. How can we then use this knowledge of constant energy for our advantage? We can express the total energy in two ways. First one is the case 1. All the energy has been stored in the compression of the spring. So the total energy of the system is half k times amplitude squared. Or we can say the total energy, we'll use the second case here, is only the kinetic energy, which is half times mv max squared. So depending on what we know, we get two useful equations. So let the first one be when we know the amplitude of the system. So rewriting this here by replacing E with this term, we get half times k a squared equals half times k x squared plus half times mv squared. Or if we use this expression for the total energy, we get half mv max squared equals half kx squared plus half mv squared. As an example, let's assume that we know what would be the amplitude of the motion. Then we can solve for the velocity v. Jumping from here, we can cancel the halves, so we get k times a squared equals k times x squared plus mv squared. And rearranging, we get mv squared equals k a squared minus k x squared. And solving for v, we get plus minus, because we're taking the square root of the whole thing. And on the other side, we have k over m a squared minus x squared. So we get this nice relationship for velocity and displacement x. We can also work further on and let's calculate what would be the maximum velocity of the motion. So that occurs in the equilibrium point when x equals 0. So in this case the x would be 0. So by using this expression we get v max equals plus minus k over m times a squared minus 0 squared, which is plus minus k over m times a. So the energy approach quite nicely wraps up the velocity and displacement. Unfortunately, it doesn't tell anything about the acceleration a, or even the maximum acceleration. To get these, we still need the sinusoidal equations from the previous section. And one more thing before we move on to the example exercise. Note that we get plus minus for the velocities also in here. And this comes from the fact that the mass can be moving to the left or to the right, so then it's up to the student to decide which sign is correct. For example, when the mass is moving to the right, which is our positive direction, we have to pick the positive velocity. And if the mass is moving to the left, then we pick the minus sign.
My crew, and that's how it went when we were kids.
I had a long john but no silver, no gold or plat. I was simply red from the years I've been holding back. With two sides to a book, I lick stamps and light matches and set fires in garbage pails and cabbage patches.